These guys are pretty good. Look how precise they are. Impressive. I'm here with members of the Marietta High School Marching Band. They're going to help us explain two important terms in physics that describe motion: vectors and scalars. In physics, we talk about motion in terms of quantities, and that's what vectors and scalars are. Let's do scalars first. They give us important information, but they're more limited in what they tell us than vectors. Scalars are quantities that are described by magnitude alone. Magnitude means a quantity, like how far, or how strong, or how much. And sometimes that's all we need to know. For instance, when we want to talk about how fast the marching band is going, that speed is a scalar quantity. They're marching at about 1.5 meters per second. It's 85 degrees out here. That's a scalar quantity too. And the tuba that the band member is carrying is about 12 kilograms. That's also a scalar quantity. Some other scalar quantities are time, like 10 seconds or 1 hour, and volume, like a cup or a quart. Got the idea? Great. So scalar quantities give us information about magnitude alone. But sometimes, and we'll need the marching band for this again, we want to describe motion in a more complex way. We want to know not only how fast something is going, but in what direction. And that is where vector quantities come in. Vector quantities tell us not only how fast we're going, but in what direction. They express magnitude as well as direction. The band is marching at 1.5 meters per second, and we're heading west. That's their velocity, which is a vector quantity, because we know both magnitude, 1.5 meters per second, and direction, west. Why is that important? Many things we talk about in physics have a direction: north, south, left, right, up, down, and a magnitude: how far, how strong, how fast, how much. When we use the Maps app on our phones or our computers, an instruction that said, "Go straight and turn," would not be very helpful. We need vector information. We need to know how far north we need to travel and which direction we need to turn. But what if we have several vectors? Like if I go one way and then another. How do we add vectors together, and what kind of information will we get? The easiest way to add vectors is with a diagram. And what that will tell us is how far and in what direction our object is going. Vector diagrams are shown as lines with an arrow showing direction, like this. We can add any two vectors, A and B, by placing the tail of B so that it meets the tip of A. The sum, A plus B, is the vector from the tail of A to the tip of B. Here, A is 11 kilometers north, and B is 11 kilometers east. See, here's the tail, and here's the tip. And when you add the vectors together, you get what we call a resultant, the result of adding vectors together. Using the Pythagorean theorem, we see that the resultant is 15.6 kilometers northeast. What would happen if we added a third vector, like 11 kilometers north? Adding all of our vectors in both the x and y direction and using the Pythagorean theorem, the resultant would still go from the tail of the first vector to the tip of the last vector, giving us a displacement vector of 24.6 kilometers northeast. Let's see how we would draw a vector diagram of our marching band and see what we find out. When they moved, the vector diagram changed. See? But some things did not change. What are they? We can move the vectors around parallel to their original position, and their magnitude and direction do not change. This becomes helpful when we have more than one vector. Let's see that now. Let's take a look at the band as they march along a coordinate plane, a graph that's formed by a horizontal number line called the x-axis and a vertical number line called the y-axis. The two axes intersect at a point called the origin. Group 1, you'll go 20 meters in the x direction and go about 1.5 meters per second. You're one vector. Group 2, go 30 meters in the y direction. You go 1.5 meters per second too. You're another vector. Ready? Go. And stop. Okay, let's get them back together. Now group 2, go 20 meters in the x direction at 1.5 meters per second, and group 1, you go 30 meters in the y direction, also at 1.5 meters per second. Now what do we see? They are back together again. So what is the resultant of the second group's movement? And what is the resultant of the first group's movement? They are the same. So it doesn't matter what order we put the vectors in, we still end up at the same point with the same resultant vector. Excellent. Nice work, guys. The length of the line determines, in this case, displacement. Vectors can be used to show other things like strength, which means how much force is present and in which direction, and lots of other concepts. So vectors give us valuable information that helps us understand many things, including how fast an object is moving and where it is going. Now you know what vectors and scalars are, and you saw how we add vectors together to get a resultant. These concepts will come into play a lot in this course, so make sure you are comfortable with them. That's it for this segment of Physics in Motion. We'll see you next time.
For more practice problems, lab activities, and note-taking guides, check out the Physics in Motion Toolkit.